All right, we are looking at section 8.6, which is taking a closer look at square roots and cubed roots. And we're looking at the homework on page 494. So starting with number 1, it says the side of a square is 16 units. So always best to just draw a quick sketch. Side of the square is 16. What's the area? The area of a square is just multiplying the side times the side. And if it's a square, all the sides are the same. So base times height, length times width, side times side. It's going to be 16 times 16. And now, since we're talking about squares and square roots, we can express 16 times 16 as 16 squared. And then you would go ahead and just multiply that out, and that is 256. That's part A. Part B, now they're telling you the area is 16. So in the picture, I'm going to draw this as 256. Area is representing everything inside that square. So now we're talking about the area inside is 16. So whatever this side is times whatever this side is. Now we know since it's a square, they're the same. So I would call them both the same variable. I wouldn't use a different variable. X times x, which we know is x squared, has to equal 16. So some number times itself is 16. So we know that that's 4. 4 times 4. If these sides were 4, you'd multiply them together and get 16. So mathematically what we're doing though is we are taking the square root of 16 and the square root of x squared. You can take the square root of both sides of the equation. The square root of x squared is x. What times itself gets you x squared? X times x. Square root of 16 is 4, because 4 times 4 is 16. Moving on to number 3. Some basic problems here. Square root of 36. So you're thinking about what number times itself gives you 36. So we should know that that's 6, because 6 squared equals 36. 6 times 6 equals 36. So the square root of 36 is 6. And I want to show you on a calculator how to do this. Now, if you don't have a graphing calculator in front of you, I'm going to show you on a phone. If you turn it sideways, you get a lot of the scientific functions here. And you can see this is your square root. So we're going to square root 36. And that's 6. All right. Number 4, square root of 121. So we need to think of a number that when you multiply it by itself, something squared gets me 121. So you probably don't know that one right off the top of your head. So if we go ahead and we just take the square root here, square root of 121, we'll get 11. So we're taking the square root of x, which is x. We're taking the square root of 121, which is 11, because 11 times 11 equals 121. 11 squared equals 121. So the square root of 121 equals 11. We need to see how that's all connected. All right, going to number 7. Taking the square root of 1,000. So these specifically say evaluate the expression to the nearest thousandth, which means unlike 36 and 121, there's not a nice whole number that multiplies into it. So if you think 6 times 6 is 36, the next whole number 7 times 7 is 49. So between 36 and 49, you've got all of these numbers that don't have a perfect square is what it's called. Okay, the perfect square, 6 squared, 36, 7 squared, 49. Everything between 36 and 49 is going to get you a decimal answer. For instance, again, we'll stick on the phone here. Square root of, let's pick a number between 36 and 49, just 40. You're not going to get a perfect number. Square root of 42. Oops, clear that out. Square root of 42. gets me this. Until I get to 49, here's 48, not a perfect number, getting closer to 7 though. So square root of 49, because 7 times 7 is 49. If you are working on a graphing calculator, you will find your square root over here. So if I turn this on, we're going to take the square root of 1,000. So I'm going to hit second, find my square root here, bring that up and put in 1,000. And again, we're not going to get a perfect number here. No number times itself, no whole number times itself. It's going to get you 1,000. So we're rounding this to the nearest thousandth. So we've got tenths, hundredths, thousandths in terms of our decimal places here. So we want the nearest thousandth. So we're going 3 decimal places. So it's 31.62. Now our thousandth place, we're going to round it. It's either going to stay a 2 or go up to a 3 based on the next number. 7 bumps it up. And so we're actually going to put the squiggles here and say it's approximately, because we did round it, it's not exact. It's approximately 31.623. So same idea on number 8. We're going to go ahead and simplify the inside here first. So this is basically the square root of 200. And if I go ahead and take the square root of 200, I get this decimal. We're going to round it off to the nearest thousandth. So we're going to go 3 decimal places. 1, 4. The 2 either stays at 2 or moves up based on the next number. The 1 says keep it the same. So that's a 2. All right, number 9. So we're multiplying square root of 5 times the square root of 5. And we can talk about a special property here that can get us right to the answer of 5. I know that this is 5. Let's talk about why. Square root of 5 times the square root of 5 is the square root of 25. You can just multiply those numbers together. And we know the square root of 25 is 5, because 5 times 5 is 25, or 5 squared is 25. So the square root of 25 is 5. So following along the same logic, okay, any number, square root times itself is just going to get you this number. We can start to see that jump. So a square root times a square root, when we're talking about the same number on the inside, just produces that number on its own, because that number times itself is going to get you the squared version of it, so 25. The squared version of 5 is 25. And then when you kind of work backwards, you're going to square root it and end up right back where you started. So once you learn the property and you see any square root times itself, we know it's just the number from the bottom. Otherwise, just go ahead and multiply it like you see it. Square root of 5 times the square root of 5 is the square root of 25. And then just go ahead and take the square root of 25, which is 5. And again, if you were still a little confused and not knowing that right off the top of your head, just punch it in. Square root of 25 is 5. All right, now we're going to apply this to the Pythagorean Theorem and some triangles. Okay, so number 12. I'm going to draw the picture real quick. We've got 11, 9, and we are solving for y out here. Now this is my 90-degree angle. It's very important that we understand that this only works in right triangles. So if we don't see that 90-degree angle, we cannot apply the Pythagorean theorem. Okay, but this works in all right triangles. And what we need to understand more than anything is that we're having these 2 legs, which come out from our 90-degree angle, and then our hypotenuse, which is out here. Whatever is across from the 90, and it's going to be the longest side, is going to be our hypotenuse. And when we have our a, our b, and our c for our Pythagorean theorem, a squared plus b squared equals c squared. The a and the b will always be the legs, and they're interchangeable. It doesn't matter which one you place in a and b, but the most important part is the hypotenuse. Across from the 90 has to be your c. So when I set this up and I plug these numbers into this equation, the a and the b can be a 9 and 11, and it doesn't matter which one you put where. So I'm just going to do 11 squared here and 9 squared here. But the order doesn't matter because you're going to square them and add them together. So it doesn't matter which order you put them in. But the c is very important. So in this case, I'm going to put the y in that spot. And so it's going to be y squared. From here now, I can solve everything down. So 11 squared is 121. 9 squared is 81. Can't do anything on the right side. I'm going to go ahead and add 121 plus 81 and get 202. So y doesn't equal 202, y squared does. Whatever y is, when I square it or times it by itself, I'm going to get 202. So that's not going to be a perfect number. There's no number times itself that gets me 202. I should say no whole number. It's going to be a decimal. So we're going to be rounding these to the nearest hundredth. So you're not going to be able to come up with this number off the top of your head. It's a decimal. So what we do is we square root both sides of the equation. The square root of y squared is y. Think about why that makes sense. Okay, what number or what variable times itself gets you y squared? It's y. Y times y gets you y squared. So the square root of y squared is y. We're just working back and forth here. And then we're just going to go ahead in the calculator and take the square root of 202. And we were to the nearest thousandth up here. Now we're to the nearest hundredth. Okay, so tenths, hundredths, 2 spots. 14.2, and then 1 is the last number. We would round it up based on the next number, but it's a 2. And so we're going to leave it 1. And since we are rounding, a squiggle is appropriate to show that this is approximate, not exact. Okay, 13. Quick sketch here. Make sure I see my 90. That's the most important part. I'm going to be solving with a squared plus b squared equals c squared. Very important to locate your a and your b. They are coming out from the 90 attached to it. And whatever's across the triangle from that, that's going to be your c. So 65 has to go in for c. These two, doesn't matter a or b. They can't go in for c. C has to be this piece, but these two are interchangeable. So I'm going to just put 39 here, and I'm going to put x here. And now I've got my equation. Now, things look a little different than they did up here. Things are in different spots. We have the hypotenuse. We're solving for one of the legs. So we're still going to go through some equation work here. So I'm going to do 39 squared, which is 1521. And then 65 squared, 4225. And now, based on everything we've done so far, you might want to start taking square roots of things right now. Okay, but what we want to do is we want to isolate the x squared like we always isolate an x. The last thing we're going to do is get that squared off of it. So I need to go ahead and just minus this 1521 to get it away from my x squared. So now it's going to say x squared equals a number, and then I can take my square root. So 4225 minus 1521, 2704. So this value here, if I take it and multiply by itself, it's going to get 2704. If I square it, x squared, it gets 2704. Probably not a nice whole number, but maybe it is. We don't know off the top of our head, most likely, what number times itself gives us this. And in general, most of the time it's a decimal, so of course you're not going to know it. So what we want to do is we want to punch this in. We're going to square root both sides. The square root of x squared is x, which is what we're looking for, just x. We don't want x squared. And if we take the square root of 2704, we do get a nice whole number, and it's 52. So we don't need a squiggle here. We didn't round anything. It is 52. And that's because 52 times 52 is what? 2704. 52 squared is 2704. So the square root of 2704 is 52. We're going back and forth, squared, square root. All right, one more Pythagorean theorem. We've got 4 over here. Here's my 90. Y is one of the legs. These are my legs coming out from the 90. And then across from my 90 is 25. So when I plug into a squared plus b squared equals c squared, I have to make sure the most important piece is c. Okay, whatever's across, whatever's the hypotenuse, has to go in for c. So 25's got to go here. The other two are interchangeable. So 4 squared plus y squared, or you could have done y squared plus 4 squared. 4 squared is 16. Leave y squared alone. 25 squared, you can plug it in your calculator. 25 times 25, 625. I want to isolate the y squared before I take a square root, so I'm minusing 16. So I'm going to take 625 and minus the 16 to get 609. So some number times itself is 609. Again, probably a decimal. So I'm going to use my calculator and square root. So square root of y squared is y, because y times y is y squared. Square root of 609 is a decimal. So this decimal times itself will give me 609. We're rounding to the nearest hundredth here, so 2 decimal places, so 24.6, and that 7 gets bumped up because right next to it's another 7. So we're going to go 24.68, and we're going to make this a squiggle because we rounded it. All right, and we're going to talk real briefly here on cubed roots. We get to 18. When this 3 is here, that's the cubed root. And what that means is what number times itself 3 times? X times x times x equals x to the third power. So if I take the cubed root of x to the third, it's x. So let's just take a random number, an easy number like 3. 3 times 3, actually I don't want to use 3 because of the third. Let's use 4 times 4 times 4. Okay, that's the same as 4 to the third. If we plug that in, 4 to the third, it's 64. So 4 to the third equals 64. That means 4 times itself 3 times. So if I take the cubed root of 64, it's asking me what number times itself 3 times gives me 64. So the cubed root of 64 is 4. So the only difference between square root and cubed root is just how many times you were multiplying the original number. Times itself 3 times, that's cubed root. 2 times squared, square root. So we want to figure out what number times itself 3 times gives us 2.197. So most likely you don't have a graphing calculator. So again, I want to show you this on a phone. And so I'm going to turn my phone sideways with the calculator, and you'll notice on mine, you might have to search for it depending on what version of a calculator you have. I only have right now a square root. So some people want to put the 3 in front like this, but that doesn't work. You notice it says 3 times this, and that's not what we want. So we're going to clear that out. So I found on my phone, and yours is probably similar, I just could find more functions by pressing this little arrow button, and cubed root is right there. I know you can't really see it, but cubed root is right here with the 3 in front of it. And when I punch that in, it actually kind of spells it out, cube root. And I'm just going to punch that number in, 2.197, and I get 1.3. And that's all you have to do. You're not expected to know that off the top of your head, but let's understand what this actually means. That means 1.3 raised to the third power is 2.197. That means if I took 1.3 times itself, not twice, but 3 times, I should get 2.197. So if I do 1.3 times 1.3 times 1.3, I end up right back where I started. Okay, so the cubed root is asking what number times itself 3 times gives us this. So 1.3 times itself 3 times gets us 2.197, which means the cubed root of 2.197 is 1.3. All right, and 19. We've got the cubed root of 45 times itself 3 times. So there's a property here, just like we knew a square root times itself twice was actually just the number. A cubed root times itself 3 times is actually just going to be the number. So my answer here is going to be 45. But let's take the steps to get there. We can multiply these together. So this is going to be 45 times 45 times 45. And it's still under the cubed root. So 91125. And we're going to go ahead and take the cubed root of that now. So again, let's jump to this, since this is more likely what you have. Make sure that you don't hit square root. You hit the cubed root of 91125. and boom, it's 45. All right, so we got to understand that this does change things. When we have the 3 out here, it's the cubed root, and it does go higher than that. You can put a 4 or a 5, and it would be asking what number times itself. 4 times gives us this. So we're going the opposite direction now of powers. So if we knew that, let's use another number. Let's say 5 raised to the 6th. Let's say we figured that number out. 5 raised to the 6th power equals 15,625. If you store one of these roots with the 6 out here, and you already knew this information, okay, this root would just be 5. Okay, because it's asking you what number times itself 6 times, which is what 5 to the 6 is, gives me this number. Okay, so we're just working in the opposite direction of a power. We're going back down to the original. And for now, we're just focused on cubed roots and, more importantly, square roots. So something squared going back then to the original base.